This is the first video on Chapter 47, Volumes of Solids. And there will be 4 videos on this chapter. In this video, I'm going to explain Theorem 351. I'm not going to state it. It's in your notes. You can look at it. It is a very long theorem, and it looks a little bit confusing when you look at it. So what I want to do is I want to explain the theorem, what it says, and why it's true. I'm not going to prove it, but I want to just sort of convince you of why this is true. In the other 3 videos, we'll do examples from the textbook. Now, before we start talking about volumes of solids from Chapter 47, let's look at some familiar volume formulas. First of all, we have a circular cylinder. So we have a base right here is a circle. The base up here is a circle of the same size. Any place that you slice the cylinder, you will see a circle of the same size. So this is a nice uniform circular cylinder. Its volume is pi r squared times the height, where r is the radius of the base. Another very familiar object is a rectangular prism. So the base is a rectangle, the top is a rectangle of the same size, and if you slice it anywhere along here, you see the same rectangle. The volume is width times length times height. Width times length is the area of the base, and then we multiply by the height. With the cylinder, we had a similar thing. Pi r squared is the area of the base, then we multiply by the height. In general, that's how you calculate the volumes of nice objects. So in general, volume is the area of the base times the height. What do I mean by nice objects, though? Well, remember what I said, you slice the cylinder here, you see the same circle. You slice this prism, you see the same rectangle. This is what I mean by nice. Now, as you've probably guessed, the solids we're looking at in Chapter 47 are not that nice. So let's look at a picture here. Here we have something that doesn't look quite as nice. We have a circle at this end, we have a smaller circle at this end, and if you slice this anywhere along here, you're going to see an object that's not necessarily the same as the other objects. They don't even have to be circles. Now, if you want to for a moment, you can imagine that this is circular all the way through. So you can sort of think of this as a flexible tube, and we can slice it any place and see a circle. But in general, that doesn't have to be the case. Now, what about the volume of this thing? It looks fairly strange. Well, imagine the x-axis running across here, and we slice it somewhere along the x-axis, and we call this representative point x sub I star. That should sound familiar. So we have an x sub I star, and we calculate the area at x sub I star. Now, if we want the volume of this little piece right here, that is approximately the area times this distance, which we'll call delta sub I. Why do I say approximately? Well, this is not uniform all the way through. So this base and this base do not have the same size. However, they're close, right? So we're just going to take the A of x sub I star, and we're going to multiply by this little distance, which we call delta sub I, and we're going to say the volume is approximately that. And it looks like a pretty good approximation from the drawing. Then we want the volume of the whole thing. So what do? We do this a lot of times. We chop this up into pieces, and we look at the areas along these pieces, and we multiply by these little delta i's. And the volume is approximately the sum of the volumes of these pieces. But not exactly, because to begin with, these were just estimates. But we don't want to necessarily approximate the volume. We want to know what the volume actually is. So what do? We take the limit as n goes to infinity, so we chop this interval up into smaller and smaller pieces. And as we did with integrals, let's pretend that we're chopping it up into n equal pieces. So these delta i's are all this distance here divided by n. So the b minus a divided by n, that's going to be our delta I. And we're going to take the limit as n goes to infinity of the sums of these volumes. and that's the volume. But what is that? That's the integral from a to b of a of x dx. Where what is a of x? It gives us the area at each place x. And so this integral is the volume. And so this is what we're going to use to calculate the volumes in the 3 examples that we're going to do from the textbook. So I've shown you what we're doing, and I've shown you why we're doing it, but what I haven't done yet is shown you how to do it. That will come in the other 3 videos.